can hear you. Thank you so much. Alrighty.
Awesome.
Yeah, so we'd like to welcome everyone to the seminar series at the University of San Francisco. The seminar series is sponsored by the Data Institute. Our speaker today is Vinay Sankarapu. He's the co-founder and CEO of Arya.ai, which was started in 2013. He has written many guest articles on responsible AI and the topic of today, which is AI governance frameworks. He was listed in Forbes Asia 30 under 30 for technology, so we're very lucky to have him with us today. Can we give a round of applause to Vinay? Thank you so much, Vinay. You can take it away.
Thank you, Victor. Yes. Thank you, Victor. Thanks, guys, for giving us the opportunity. I hope you are enjoying the day. So let me quickly start with briefly introducing what we do, and then I'll jump into today's topic. As introduced, my name is Vinay, and I'm the CEO and founder for Arya.ai. What we are solving is we are building a verticalized AI cloud for banks, financial services, and insurance. So we are focusing primarily in the BFSI industry, as people call it as. So within that vertical, we wanted to build layers on top of the models that can enable the end user to deploy and scale models more actively and in a responsible manner. And while we are deploying these models, one of the common areas where we see a lot of interest is around responsible and explainable AI. For most of the people, it's like a post-facto thought process wherein they will build a model and then they'll think about okay, I have a model, so how do I enable explainability around it, or how do I enable monitoring around it, and all of that. But we believe that this has to be part of the design. When somebody is building a model which is meant for a purpose, particularly in high-risk environments, you are actually replacing some of the expert functions in that process. It could be a diagnosis recommendation, it could be an underwriter, or it could be autonomous car, for example. So you intrinsically carry a responsibility to the end customer when you're building these models. Now, there is a lot of questions on, is it safe to use your model, or what are the risks that are associated with these models and all. So this is where ML observability can help not only the builder, but also the user to ensure that all the associated risks of deploying this model is managed by having such framework. So ML observability as a layer is kind of independent as compared to your base MLOps layer. Your base MLOps layer covers a lot of recurring activities like data preparation, model building, model retraining and all. ML observability typically comes a layer on top of MLOps, which is very niche. So which helps you to monitor the models, explain them, or audit them, that as a separate layer of deliverables itself. So we'll go into the details of the ML observability and give you some examples about realistic scenarios on why we needed it and how we implemented it. So in today's conversation, I'll spend time primarily around introducing ML observability. What are the components that would be required for a good ML observability framework? And we'll go into the deep dive of these components, and probably if time permits, we will walk through a case study as well. Now, so if you look at deploying AI, particularly in high-risk use cases, right? Typically, the expectations are, so you are deploying it for, let's say, diagnosis recommendation, or as I said, the underwriter, or those kind of functionalities. The basic expectation is it should be there should be a transparency to the end user, so that the end user should be able to understand what exactly happening inside the model. Because as these are high-risk use cases, they cannot use simply a black box model. Second is bounded risk. Bounded risk is, if I use this model, I should know what is the risk that I'm kind of adding to my process. The problem with this is, or at least the challenge with this is, currently models are not fully tested nor stress tested, because of which there is no definitive promise of bounded risk. What I mean by that is, somebody will build a model and they simply productionize it without doing enough stress testing. So whenever there is some issue with the model, then people start correcting those things. And there is no cap, or there is no constructive analysis or estimation on what is the risk of using those models. But this is actually a basic expectation when a user is looking at deploying AI for high-risk use cases. Third is promised SLAs. Promised SLAs is, let's say you build a model and your model performance during or initial production is very, very high. You promise that, or at least you showcase that your model is 98% accurate on test data. But is that accuracy consistent over a period amount of time? If not, then what is the turnaround for that, right? But if you're actually deploying, again, AI for high-risk use cases, so people expect that there is a consistency in the process, there is consistency in the model. For example, let's say you're deploying AI for autonomous cars. What you are saying is, in the first 3 months of using the autonomous cars, you will have the best driver. And then after 3 months, the driver quality will degrade, and we don't know what kind of activity will happen. So that kind of inconsistency is not at all permissible in high-risk use cases. Fourth is the auditability, right? So, okay, you deployed the model for some of the use case and something went wrong. Again, let's take an autonomous car as an example. So there were many scenarios where when Tesla has crashed, then there is a regulatory audit, legal audit to figure out what exactly happened, what exactly has happened, what is the source of the error, or who is the reason behind the error and all of that. So there have to be auditability in such solutions, or else by regulations, it's not acceptable to be used in such use cases. And fifth is a compliant, right? Meaning now the regulations are becoming slowly clearer in few of the geographies, at least if not all the geographies. So for example, the simpler compliance factor is non-bias, meaning you cannot use biased models for some of these use cases. So how do you promise that whatever the model that you are deploying is compliant? So these are the specifications of broad framework in terms of if you're deploying AI for high-risk use case. Now let's try to understand why these are required, right? And what is the reality of the AI models? First thing is, can the models fail in production? Actually, yes. The reality is models fail more often as compared to the comparison as a software, right? As compared to a software, models actually fail more often and more frequently as well. The expectation is, the businesses could expect that once I deploy the model, the initial model accuracy will remain same. But actually, the model accuracy or performance will be drifting or degrading actually. At a macro level, at a higher picture, it will be degrading much faster, whereas in micro time frames, it may be degrading in a small intervals. So this is the reality. Your model, when you put that model in production, your model quality and your model performance will be degrading. There are various reasons behind that. We can discuss that as well. Now, there is a paper published which had actually tracked this across multiple experiments. When they have done close to 20,000 plus experiments and tracked the error performance, over time what we have observed is the error variability was kind of more diversified. Meaning there are more errors and more diversified errors over time. So model quality is degrading much faster and much effectively as well. Their conclusion was almost in 91% of the cases, the model degradation is happening. In fact, the reality is it will degrade for sure, but how much, what is the quantum is actually dependent on various things. For example, as basic as what is the quality of the data that is continued to be supplied to the model during production. And second is, of course, how the model is built itself. While this is on a broad set of models, actually we did a quick benchmarking with lending club datasets. Lending club data is one of the prominent underwriting datasets. In this case, what we have done is, in lending club data, you will have datasets from 27 to 2020 actually. So you have the dataset for almost 11 years. So what we have done is, we have assumed that the model is trained from 27 to 2014, and then we use the model for remaining years. So similarly, we have trained the model on 7 to 15 and tested it on the remaining years, 7 to 16, 7 to 17, and 7 to 18. So you see the trend, right? The more frequent the model training was, or the more recent the model training was, the better was the accuracy. And same thing with MCC or recall or precision scores as well. So there is a better accuracy and better precision of recall if you're training the model more frequently. And again, so what is the time frame that you have to train, or what kind of data to be included as part of the retraining process is a very much problem-specific kind of analysis. But net on conclusion, you can see that the model degradation is a realistic phenomenon. In fact, you can test it by yourself as well by using this learning club datasets. Now let's understand why the model degradation happens, right? One is when you put the model in production, you're actually putting the model for a lot of uncertainty. Meaning when you are training the model, you have a lot of control on what data is going into the model, how the data is going into it, what is the cleanliness of the data. But when you put it in production, there are n number of scenarios the model may or may not have seen. In all those scenarios, the model may not be performing ideally as per our expectations. Second is data drift itself. So your data that you have captured itself might be changing over time. So data drift actually has a very strong impact on model performance. And the third is concept drift or model drift, meaning the target of the model itself will be changing, right? A classic example for this scenario is during the COVID times. So before COVID and after COVID, the ideal profile of a customer, depending on the products and all, has actually changed a lot. It could be a financial product, it could be a medical product, there is a lot of change. So the goalpost, which is your target of the model itself, might be changing as well. And there could be an adversarial attacks as well. So meaning nowadays we are seeing this more often. The attackers are becoming more smarter in terms of leveraging the models and leveraging the gaps in the models and try to get illegal kind of activities around it. So these are the high-level reasons on why the model degradation would happen. Again, just to recall data drift. So data drift is the actual data itself could be changing. For example, a simplistic thing is the metric value, right? Let's say in your training data, the metric value is meters, for example, whereas in production, suddenly there is a case where the metric was centimeters, for example, right? It's a very simplistic example, but there could be a lot more complex examples as well. And then the concept drift, as I said, the target itself might be changing. So, are these hypothetical problems? Have you not seen this in reality? Actually, yes, we have seen many examples in the recent times. One of the recent examples was with Equifax. Equifax is the credit bureau platform. So their core business is in credit scoring models, right? It was observed that there was a model drift and it was not tracked, and they started giving wrong credit scores for close to 300,000 plus customers. And then later on they figured out that there was a model drift and they corrected it afterwards. So this is one classic example where you deploy a model, you're not tracking it, and then you realize that the model actually is giving you wrong predictions after some point of time. So typically in financial products, this happens when you have a feedback outcome. For example, if it is underwriting, it could be NPAs. If it is insurance, it could be claim ratios. Basis on those, you would have multiple realistic metrics that comes back to you and tell you that your performance actually is bad. So another example was Zillow. Zillow was using AI/ML for price prediction, house price prediction. Again, this was during the COVID times where the actual house price, the ideal house price, has drastically changed, right? The asset could remain the same, but the purchasable price of that asset is actually drastically different as compared to pre-COVID and post-COVID. So this is the concept drift example, right? They started as the model was doing, as the model was prone for concept drift, target drift. The model was actually giving wrong predictions, and the bets were made on those wrong predictions, and then they later on realized heavy losses because of this. So these are not just hypothetical examples anymore. These are very realistic examples. So whenever you are deploying a model in production, particularly in high risk use cases, you will see these problems very often. Now, the other challenge that we see is fairness and bias, right? So this is again, as I said, this is one of the very fundamental requirement as per the regulations as well. Now the assumption is, okay, I'll do some kind of fairness analysis by tracking, let's say, false positive parity or some kind of metric, and ensure that model is trained properly without any bias during the training time. But the question is it enough? Meaning, you may have not considered the sensitive features in your model. There could be correlative factors, right? For example, the same paper that I talked about earlier, it was observed that the fairness also is varying over time period, meaning the bias has observed in certain time periods, whereas it is not observed in certain time periods. So, which is fairness and bias is actually a temporal problem. It's not a one-time problem. You could have an uninduced bias because of external factors, which means you now have to track that metrics as well. If you are deploying such models, one thing is you are tracking it for data drift and model drift, but you should also start tracking it for fairness and bias. And again, you have examples like Apple Card underwriting, where it was purposefully leaning towards males as compared to females in terms of underwriting capacity and other thing. But again, this is a very common, sometimes identified, sometimes unidentified problem in AI models today. We talked about the model level aspects, right? The monitoring level aspects. Now let's talk about the explainability of it. When you have a model prediction, so it could be something like this. You have a model output, like let's say if it is a classification, you would have a class and the confidence score, or if it is a regression problem, you would have some kind of numerical output, right? So this is your model output. Now you are sharing this to end user. Again, end user is, let's say, a doctor, for example, or a claim assessor or an underwriter. So when they see this output, there is absolutely no confidence on this output unless you start explaining it to that user. For example, let's say I'm using this model for diagnosis recommendation, and the model is saying you have to start diagnosing for heart-related conditions. A doctor would be perplexed to see that why a model is giving me this recommendation. It is clueless to give me this recommendation. Unless you explain how the model is functioning, the prediction actually do not carry enough weightage. Again, this goes back to the high-risk use cases. You need to start explaining it, and second is you need to start explaining it in a manner that the end user can understand it. What I mean by that is, you have multiple stakeholders in the process, right? So whenever I ask a data scientist, what kind of explainability that you would use, they would immediately say that I use sharp, I use line to create feature importance. And the next question is how many people understand feature importance? You are creating feature importance as an explainability, great, but who can understand that? Only a data scientist, right? If you give that to a doctor, he would say, fine, it gives me some feature and feature weightage. What next? How do I interpret that, right? The interpretability is actually very contextual in nature. The context is depending on the guy who is eventually consuming it. So you would have multiple stakeholders. When you're building the model, you have to ensure that it is explainable to all these stakeholders, but not simply skewed towards the data science teams or the experts in that process, but it has to be understandable to everyone. And when it comes to explainability, there is this inverse relationship, right? Meaning the more complex the model is, the tougher to explain those models. Again, it's debatable, meaning you could use intrinsically explainable models like XGBs, for example, those kind of models. Or if you actually want to use deep learning, there are alternate methods to explain those techniques today. But again, one of the things that we realized was your explainability has to be consistent. In fact, I'll show you an example where there is a scenario where people can fool such explainability systems as well. So coming back to explainability, I think when you're doing explainability, you have to remember two things. One is how accurate is your explainability, And second, how interpretable is your explainability? Is it understandable by everybody in the stakeholder? Now let's talk about auditing, right? So, okay, I've given you a scenario like autonomous cars, for example. Something went wrong. Then how do you audit those models? How can I make sure that this is auditable and I can explain what actually went wrong inside the model? So if you look at typical auditing process is primarily related to business processes, right? For example, you have all these 4 large consulting firms which are skilled in doing auditing like taxation, business process or regulations. So they can figure out a process gap. But how do they figure out a gap in a model? They do not have the skill set to do auditing. And on the counter, currently businesses, when they do auditing, they only involve the operation folk because again, the current definition of auditing is primarily related to business and processes. But as we go forward, as the models are becoming more key to the business, meaning you would probably be underwriting more with a model than a human in the flow, then you have to start doing the auditing in a very different manner. So auditing should involve machine learning guys and data scientists who has built that model and able to provide different reports, not just at a model level, but also at a case level. Meaning, for a given prediction, can you give me these things? So auditability should be ensured for the model and each prediction given by the model. So that's the job of the MLEs and DS. We are slowly seeing this becoming the responsibilities of the data science teams. And also the auditing teams are now upskilling their expertise in ability to do auditing related to models and everything. So this is already happening today. Again, the top 4 consulting firms are now building skill set to do auditing on models and model safety and model accuracy. If you are planning to join in an environment which is highly regulated, like banks, financial services, insurers, Medicare, manufacturing, or those kind of areas, you are now expected to have an auditable process and models that are auditable. Using any kind of explainability, is it enough to prove that you are actually doing everything is required? So what is happening is, as I said earlier, you may be using sharp or line, for example, as your explainability method to deliver the auditability. But the problem is, people can actually use scaffolding attacks to fool sharp and line. So one of the attack was, I may be using a biased, a sensitive feature in my model. But when I'm deriving explainability, I can actually hide that feature and show that for a regulator or for an auditor that I'm not using any kind of biased models. So sharp and line, if you're using them for explainability, they're actually not that accurate or consistent as people are expecting out of it. So there are ways to fool that and then attack those kind of systems as well. In fact, there is a paper that talks about this called fooling line and sharp, and this is attacks on post-hoc explanation methods. Feel free to read the paper, and then there is a lot of detailing that went into it on how to fool such kind of systems. Okay, so we talked about scenarios of monitoring, scenarios of bias, scenarios of explainability and auditability, right? Now there is a new problem when people use AI and models, which is data privacy and data safety. So this is particularly prominent if you are using any kind of generative or synthetic AI models. So for example, if I have a very sensitive data, but I want models to be built, one is I can either use the data as is and build ML models. So for example, let's say I'm trying to build some kind of generative AI model, maybe an LLM, for example. I've used actual textual data, very sensitive textual data, and build a model, right? Now you have seen enough case studies where these LLMs are leaking sensitive information to the end user. It's not only LLMs, but also generative image models as well. For example, stable diffusion. For example, there was an example where The stable diffusion models are creating images which has the bookmark inside the image. So using the prompt attacks and those kind of things, I can actually start attacking the models and getting sensitive data out of these ML models. So if you use the data as is, this is the problem where the model could leak your data. The other counter solution is anonymizing the data and building the models on anonymized data sets, right? That is the immediate solution for it. But again, the problem is even depending upon what kind of anonymization that you have done, they are also prone to attacks, for example. So one of the examples was, when the movie review data was published by Netflix. So what people have done is they have used peripheral data, which was Amazon reviews, and try to localize the customers who is there in Netflix, for example, even though it was anonymized. So this problem is actually becoming more prominent as people are using more and more such generative AI and synthetic AI models. So this is another challenge, right? Another possibility of model rust. So we talked about n number of scenarios. The conclusion is, are all models safe to use? Meaning you could build a model in half an hour's time. You could build a model maybe taking 6 months' time, but you may be showcasing very great accuracies, very great consistencies and performance. But is it qualified to go production, right? That's the question now everybody is asking. You had spent quite a good amount of time. Is it qualified to go to production? Unless you actually address the problems that I mentioned earlier, the most probable answer is no. Not every model is deserved to go production because it has to be addressing those issues that are there along with the model. Then it is acceptable to go to production. So another way to solve this problem is creating a policies layer, right? Policies layer is instead of using the model output as is, which would have a lot of issues, I'll actually create an intermediary layer where I would start defining my policies and these predictions go through the policies before it is given to the end user. So this policies as a solution is also becoming very prominent, and it's already being used in BFSI industry, for example, wherein these policies can be as simple as, I do not want the model to decide on a transaction which is very high in value, for example, because I want to manage my risk. If the model fails, these policies could become my guardrails to prevent any major losses, right? Now, if policies is something that people are looking more actively, the immediate thing that people also need to look at identifying such policies which are contextually relevant for your model, right? Meaning, let's say I have ABC policy for a model A, such ABC policies may not be relevant for model B, right? Because your new model may have different kind of risks. Then you need model-specific policies. So to be able to define that model-specific policies, you have to do stress testing. You have to test your models across scenarios, across conditions to figure out what are the gaps that are there in your model, and then start filling in those gaps using these policy layers. So net-net, there are a bunch of more things as well, but these are very prominent issues that we have seen. One is tracking the models in production, so that you know that when the model degradation is happening ahead of the time, and you can deploy a solution which could be retraining or retraining on a very contextualized sample set. Next is bias. Bias monitoring is not a one-time activity, as the paper suggested. It's actually a temporal feature, so it could actually come in at different time periods. So which means you should also start tracking bias monitoring as well. Third is auditing. Ensure that your models are auditable and ensure that whatever the methods that you are using to deliver that auditability are true to model and more accurate, like the explainability, as I said, using sharpened line may or may not be the ideal explainability methods based on the use case. Next is the policy layers and the model leakages, for example. While these are the challenges, there are added challenges, particularly in high-risk use cases, right? Particularly in these regulated environments. One is you may not get the feedback more actively. So, for example, let's say I deployed a model for underwriting. I'll only know the model performance after 6 months, after 12 months, after 36 months. When the asset becomes bad, that's a feedback to the model that, okay, I've acted right or acted wrong. So sometimes your feedback could be very, very delayed. Next is, any explanation is not the right explanation. In fact, wrong explanations can actually cause more damage than having no explanation. As I said, if you're using sharpened line and building explainability basis on that, even if you change perturbation, for example, if you're using line, you would have two different explanations for the same case, for the same model. If there is a change in ownership of the model for the same use case, you would have two different explainability. That's actually going to be more conflicting in nature than providing any kind of explanation. Next is inferencing. Such explainability should be understandable by all the stakeholders and all. So it's not quite easy problem to solve. So all these challenges makes things much more complex than what it is today. So this is where ML observability is supposed to build that layer, right? ML observability is supposed to give that directional add-on top of the ML ops layer. So typically, ML observability comes in when once you have a model in place. So for example, this is the most high-level architecture of horizontal ML ops, where it starts from data cleaning to model deployment. Now, ML observability will be looking at model selection and production activities, right? At the same time, ML observability should start involving all the stakeholders. Meaning, if MLOps is dedicated to data science teams and MLEs, ML observability is the communication layer between the data science teams and the business teams. It is the intersection of where the production and the business meets in one place. In that case, you would need to have ML observability, including monitoring business usage and acceptance, regulatory acceptance, model risk maintenance, and model feedback collection. So these activities are soon becoming the unique layers on top of MLOps and are becoming the part of ML observability frameworks. Traditionally, or at least currently, ML observability is only looking at model monitoring in some examples wherever we have seen it is being implemented. But we believe that ML observability has to go beyond that. It has to take the responsibility of the business, the user, and the society as well, which is the regulations, such that a good ML observability will become a good starting point for AI governance. Now, let's say we are deploying it for a lending use case. Lending is a classic use case that this is prominently used today. If the builders are data science teams, implementation teams are IT and engineering, for example, or it could be third-party guys, and the users are underwriters, head of departments, auditors, risk managers, and regulators, right? So these are the users of the model. So ML observability will become the communication layer between them to deliver these section of activities. Now, this is where we operate as a product. So we have a product called Arya.ai, which is the ML observability platform. This is not, of course, this is not a lecture to promote the product, but I'll just quickly give you the background and then I'll go to the case study. So what we have done is we picked up these components, which is explainability, monitoring, auditing, and policies, as the components of ML observability. Is what we are offering as a separate layer, which sits on top of your MLOps. So this is what Arya does. You can only remember that Arya.ai does explainability, monitoring, auditing, and all of this stuff. Now let's take in a case study, right? So in one of the customer, we deployed this lending module where we were using DL, deep learning, where we were giving this prediction, right? As I said, the question was, is this enough? Is this enough for the end user? The answer is no. You have to give additional explainability for this prediction to be acceptable by all the stakeholders. So the immediate thing that we did was, let's deploy XAI method to do this. In this case, we have our own proprietary method called backtrace. Of course, Arya.ai supports sharp line, but we also have our own proprietary method called backtrace, specific to decoming models, because we wanted to have more accurate and more consistent explainability, which we couldn't satisfactorily get from sharp line. So we used backtrace to create these feature importance. Now, as I said, so feature importance fine, but is it understandable, interpretable by all stakeholders? The answer is no. So what else can we do? What other explainability can we do? Next, we thought of something called references as explanations, meaning, so let's say something like this. This is a classic example, right? Let's say you have a question and you use some kind of LLM, ChatGPT, or the other competitive LLMs that are there today. So when you ask a question, it gives you an answer. I'm giving you three scenarios. In this case, there is a question, there is an answer, and there is references, right? This is one response. In another response, there is a question and there is answer. So, and in third response, there is a question, there is an answer, there is references, a bunch of them. These are primarily the internet articles. When I ask a question, so which one would you trust more? Most of the times the answer is probably I trust the answer that has references, right? Because when I look at the answers, I would validate the references. If references are good enough, then I trust the answer. So that's the outcome of this experiment, right? While the answer, that is definitely matters. But the evidence or the references where the answer is derived from also matters a lot. Now let's take this concept and apply to lending, for example, right? Whenever a prediction is given by the model, how do we give references? How do we can tell the user that this is where the model has learned and this is why the model prediction is that. So to do that, what we have done is we have deployed a technique called references as explanations. What we did was we compared the feature importance of the current case with the feature importance of the past training data, and we localized the policies where there is a high similarity between the feature importance of the current case and feature importance of the training data. So the assumption is whatever the model is giving this prediction would have actually came from this 20 past policies, right? Now, whenever a prediction is given by the model, it also gives a reference samples from the past where the model would have learned this prediction. Now, this is fantastic for a user. So, for example, underwriting as a use case again, right? So, model is saying, let's say this case to be rejected, or this case is a very high risk case. Now they can validate it by looking at the references. In the references, let's say if majority were rejected or some of them were rejected and very similar to the current case, they can validate it by looking at what has happened from the past. So this has become one of the powerful evidences for us, explainability for us, references as explanations. The same is actually used in images as well. So prototypes as explanations, for example. There are multiple techniques to use prototypes as explanations. In this case, as it is a tabular data, we are using feature importance similarity as one of the techniques to use similar cases. Now, this is actually helping us in another scenario as well. So, whenever you ask a business about the confidence of the training data, there is always a question of labeling error. Meaning, let's say, in the past, there are 100 underwriters. Not all of them carry a near similar or a similar kind of expertise, right? So some of the underwriters would have been really good, some of the underwriters are really bad, which means that there is a labeling error on the past training data. Now, so you looking at these similar cases, they can actually validate those labeling errors as well. So references as explanations is actually one of the easiest way to explain the model prediction. It's simply saying that this is how it has happened from the past. So model has learned that outcome, and now it is saying similarly like this as well. So this is second type of explainability, where we are using references as explanations. Even after doing these two things, we still had challenges to convince the user, saying that okay, I get all of this. The comment that we have received from the experts was, No, you are saying feature importance, you are giving me similar cases, both of them are fine, but is it actually working in a manner that I would do? I would do my job. Let's say my job is underwriting again. I would do things in ABC manner, which is my principles of my job execution, right? Let's say you are an auditor, you are an underwriter, you are a data scientist. You would have your own principles of your job execution. The expert or the user want to see a correlation between the principles of execution of that function vis-a-vis with the model outcome. So for example, let's say you can take an example of a doctor. Let's say you built a model for diagnosis recommendation, right? When you do diagnosis recommendation, let's say the model prediction was to do again, let's say heart-related conditions. Now, a doctor would ask that on what basis have you done this? You may say that these are the features, these are the similar cases. Okay, fine. But I would recommend a heart-related diagnosis if I see some ABC things. ABC is, let's say, A, age greater than 45. B, had a recent symptom of chest pain or numbness on the shoulder, for example. If I see such frequent chest pain or numbness or something like that, then I will immediately go for recommending for a heart-related condition, right? So what necessarily they are saying is, these are my top 2-3 important principles to take this action. Is the model considering those principles as the top principles or not? So this is where we could see a lot of debate between the model prediction and the expert. You can think of expert being any expert in any process. Doctors, underwriters, claim assessors, product recommendation guides, or autonomous cars, which is drivers, for example. In any of those scenarios, they would want to see a correlation of the principles of the business or the principles of the job vis-a-vis with model functionality. So how do we show this in a model, right? So we have done a neat technique. So what we have done is, before we deploy the product, we asked the user a bunch of principles that they would follow. They need not to rank it. We just ask them, what are the different principles that you would do while executing this job? For example, doctor, right? So what are the different things that you would do while recommending a diagnosis? So they would say that I will look for frequency, by some nuances are chest pain, age, I'll look for diagnostic factors, blah, 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 blah. So they may list out maybe 100 principles, 150 principles, or 250 principles. It's fine, it doesn't matter. So now what we have done is we try to figure out what are the features that would have been used in that principle. For example, let's say one principle is, this is for underwriting, if there are any public bankruptcy disclosures and low FICO score, it's not a preferred case for an underwriter. They will definitely reject that case. So these are the high priority principles for rejecting a case. So for this principle, it is built on 2 feature set, right? In this case, there are 3 features which are relevant to this. There is a feature in lending club data called public record bankruptcies. This is a feature name, and FICO range high, FICO range low. So what we have done is, we linked this principle with these features. And these features intrinsically has feature importance, right? We are anyways doing the feature importance for all these features. And then we combined these features which are relevant to this principle and define that as a total feature importance score for this one. In short, if I can link this feature to a principle, feature importance is anyways additive in nature. So this statement, I can start ranking the principle that is being used in that prediction, right? So our Arya.ai has an interface where you can simply define this, write these principles or observations as we call it as, link those observations with features, and the framework automatically finds the feature importance and creates the feature importance score for all these principles. So for example, you could see on this extreme right end, you could see these are different principles and the feature importance of these principles. Now, when an underwriter looks at this case, they may say that, okay, the applicant has good FICO score. This is one of the top principle for them to accept an underwriting policy. In this case, this is actually the top principle based on the feature importance addition, right? Again, I'm not saying that this will reflect the model functionality in a more accurate sense, but if you actually did the feature importance which is true to the model, again, which is coming back to your explainability method, right? Instead of using surrogate methods, if you use model-specific or more accurate explainability, these could actually be very closely correlate to the model prediction and the business functional principles. So this actually combined is what as an explainability. Now you have feature importance, simple textual explanations, references as explanations as combined. Any underwriter, any doctor, any user can actually understand this combination. Of course, there is a little bit of knowledge skill share that has to be done, but once they do that, this seems to be an acceptable template, at least so far wherever we have experimented. This is actually accepted by the users as one of the acceptable explainabilities for the models. So this is one thing that we were able to deliver using Arya.ai. Now Arya.ai becomes a plug and play, so it can be plugged into any kind of model, any kind of MLOps framework, and you can do all of these from the UI today. And soon we will enable an SDK to do this from your notebook as well. So that is one part of it, right? Explainability. So if you look at in this explainability itself, it's not an independent activity anymore. On one end, you have data science teams. On one end, you have business teams who are collaborating and creating which is an acceptable explainability template. This is what is required to make sure that the stakeholders are participating in the process of building an AI solution. So this is what we believe will make or will build confidence and trust in the process. And then to do data drift and concept drift monitoring, again, we were able to create multiple metrics to do data drift and concept drift. There are actually more than one way to do data drift and particularly data drift monitoring. It could be PSI, KL divergence, chi-square test, chi-square test. So there are multiple matrices that you can use. Now this is where the data scientist actually has to experiment on what threshold makes sense for them and what test makes sense for them. Rule of thumb, you can use PSI, but many times we have seen that instead of PSI, the other matrices could have more effective way of tracking data drifts specific to a model. So this is where data scientist has to experiment and figure out what kind of metrics make sense. Again, the rule of thumb is you definitely have to monitor the features which are high importance, which you can get from global feature importance, right? So you will know that what are the top 20 features which has the most high weightage in terms of model prediction. So you track them, or you track the entire data and figure out whether there is a data drift or data set drift, those two features. Same thing with target drift, so you can use these similar matrices as well. PSI again applies for both of them. It works well in most of the cases, but do experiment with other techniques and try to come up with new approaches as well. And then for bias monitoring, we are using things like false positive rates, false negative rates, and then we compare it with the sensitive class. So for example, let's say you have a gender, so we compare it between male, female, and others, for example, and try to do a correlation and gap analysis there. To do the model risk and policy creation, right? So we have deployed a technique called model-specific policies and process-specific policies. So model-specific policies is when we build a model, we try to analyze and create segments where model performance is obviously not up to the benchmark. Let's say benchmark for my model performance is 98% accuracy, right? I can actually segment my data and find multiple segments where the model accuracy is not met. And for these segments where model performance is not met and I see a high probability of false positives, I deviate the model prediction for those segments. So these segments can be done by doing a data analysis, or other technique that we have used is rule fit model. Rule fit is nothing but creating these boundary conditions which is related to the target, right? You could actually define your false positives as a target for the rule fit model or true positives for the rule fit model, depending upon what you are building. And you can come up with multiple policies that you can implement to prevent obvious model errors. This is one thing that we have done. And second thing that we have done is data-specific policies, meaning if some data points are very sensitive, very important, then we started defining data-specific policies for those as well. So these policies are necessarily qualifying whether the model should pass on the prediction as is, or the policy should override the model prediction in a manner of some sorts. So this is one segment of creating the policies. Second segment is it could be an obvious process-driven policies, right? So for example, as a business, I do not want to accept low FICO scores, for example. Then I define what is a criteria of FICO range. Then if the criteria is anything below that, I don't care about model prediction. I simply deny that case. It could be as simple as those. Or it could be something which is related to model and process combination. For example, let's say you have a regulation that you cannot have a biased predictions. Then you have to generate that as a data point for these policies and create policies for that. Like whenever there is a bias, don't trigger the model prediction. For example, whenever there is a data leakage observed in the model, then don't use model prediction at all. All in all, as I said, going back to the model stress testing. So you have to stress test your model to identify all of such policies, and your model should have these guardrails, and then only your model should be deployed. In fact, this is actually very, very well adapted technique in ChatGPT, for example. You may have seen that earlier ChatGPT versions were more biased, more erratic. Whereas as the prompting is nothing but the guidelines, right? You can actually define the guardrails in the prompting. As the prompting becomes more prominent, you would see more stabilized responses. Same thing happened with Bing or ChatGPT or any other LLM today. As prompting became famous, now people are observing that, okay, this is something that I can even do for tabular models, not just for LLMs, for example. So we have actually created a framework to define these policies around your model. So we become the layer of the protection, or you can call it as the security layer on top of the model. Whenever the policies are triggered, the policies can override the model prediction. So all in all, this is what we have done in our case of case study, where while we have built a model, we have done, summarizing it. Explainability, we have started off with feature importance, but we wanted more accurate feature importance, so we used our own proprietary method. Second kind of explainability that we have done is references as explanations, which is showing examples of similar cases from the past, such that the user can easily correlate with it. The third explainability was finding a way to correlate between the business principles and model functioning. And from monitoring standpoint, we have done data monitoring, but we also have used multiple matrices instead of using only one metric. And we validated which metric makes sense, and we started using that metric as a monitoring metric for our data drift and target drift. And then to be able to build policies for the model, we have done stress testing, we have done analysis of segments where the model performance is not up to the mark, and we understood what is the business acceptance criteria, and we understood what is the compliance criteria, and added that as part of our policies. So this is netted is what we have done in this lending case study, in this case, as I said, if you look at the stakeholders that are involved, there is data science teams that is obviously involved. The engineering team is actually owning the policies layer. They were able to add policies, remove policies, and all of it. The business teams are actually involved in getting that explainability template right, such that it is acceptable not just to them but also to all the other stakeholders. So this is one of the ways that You could use a good ML observability tool to ensure that it's safe, it's auditable, it's understandable by everyone, and you are protecting the business from the risk of model failure. So this is what we have done in this example. I can actually quickly show a quick walkthrough of the product as well. Yeah, so let me quickly show a quick example of what users can do. So this is one example where I'm using quick methods of building model. Now this is what many people are doing today, right? Use some AutoML and build model. In this case, I've loaded my lending club dataset, and to clean and prepare the data, I'm using Klib library. As I said, the agenda of this notebook is how quickly it is now to build a model, and then use Arya.ai to make sure that it is an acceptable model. So once I loaded the data, I used Klib to clean the data. So my data is prepared. Then I passed that data to the AutoGlone model. AutoGlone is the library that we use to build, in this case, the AutoML model. Once the model is built, then I looked at my false positives. So I had 27 false positives in my testing data. I have actually passed on these samples to my Arya.ai project. So here I can see all these details that I've done in my notebook. So these are my different testing data. I've done few API calls as well. So I can actually open a case. Okay. So here you could see different things for that case. Just taking time to load. Yeah, so here is an example of a case where you could see feature importance, you could see the observations that I've added. Now I can see the feature importance score for each and every observation. So for example, in this case, the applicant has less than 5% revolving utilization. It has 0.3% score that is unnecessary coming from the feature importance, for example. And then here I can see the policies. Policies are added here. So model prediction and final decision. So if the policy is triggered, then the model prediction will change. So I built all these layers in Arya.ai, and then from monitoring standpoint, also I created these dashboards for the top features, for example. So here I can see the data drips in this case, for example. Well, this is a monitoring layer and everything. So what I can do from model improvement, right? So I noticed that these are my 27 false positives. Now what I've done is I passed those false positives to Arya.ai. Once I pass them, then this is my explainability that I received from one of the false positive case. So this is my false positive case. So here I can see my observations, which is in simple text. These are my feature importance. In fact, you could see those details here as well. So even though I had a false positive, the final prediction is actually changed to manual. It is changed to manual because the policies got triggered. So actually this was a false positive case, but as the business defined the policies on this, now even if I deploy that model, this case would have gone to manual instead of going as a straight through or an automation kind of case. So this is a feedback to the data scientist, right? Okay, I built a model. Now some of the predictions were safeguarded because the business already defined the guidelines in Arya.ai. Now they can do two things. One, they can continue to use this in production, or they can take this feedback and they can look at what policy is triggered, and they can make modifications related to these policy, right? This is how it will work. We believe that this is how it will work going forward. Whenever somebody is building an AI/ML product, you would have a product team or business team who defines observations and policies, and then you will have the data science teams who builds models. Models will get the feedback from the observations and policies, and vice versa. The observations and policies will get the feedback from the model. So building an AI solution is not going to start from model building anymore. It will be an intersection of the business expert plus the data scientist. There is a credit that can be given to a data scientist, but to be honest, data scientist is not an underwriter. Most of the times, data scientists do not have any knowledge on the problem. Maths is not the answer to a problem, right? Maths is a direction. You have to use maths and then use art and science to be able to use the outcome of it and become usable. So this is what Observability can deliver. It can combine the business expertise and the model outcomes and the data science expertise to create a balanced AI solution. So I think this is pretty much it. I have talked a ton of things. Yeah, I'm open to questions. Happy to answer if you have any questions around these kinds.
Thank you very much. Okay, at this time we'll take questions from the audience if anyone would like to ask. We have 2 mics here. I will just turn them on. Can you make sure that's on? No?
Hello? Hello? Yep, good? Yeah. Okay. So there was kind of a long discussion here about just building trust with AI models and the importance of explainability to get stakeholders on board. My question for you is this question a question for yesteryear? And because what you've talked about in these examples, and you showed 3 examples of ChatGPT or an LLM, and how the third one had links and citations, and how that one might be the preferred one, for instance. But increasingly so, you've shown examples of people who kind of get served AI models and you have to build trust with them. But in, say, the ChatGPT space and in increasingly more applications, people aren't being served and serve these things. They're actually actively going to platforms like ChatGPT and as a result engaging in their own automation bias and perhaps even replacing this traditional bar of trust with, I already trust this because I have certain degrees of automation bias. So my question for you is, in the future, will explainable ML for users be useful, be interesting, or will it instead be more related around automation bias and these other kinds of things?
Yeah, okay. Awesome. I think explainable AI has been there for the past 5-6 years, right? And it has been one of the prominent topics on having explainable, model predictions. Now, ChatGPT is kind of educated everyone that you can do a ton of things. Now, what's actually happening is many business users, particularly who are using AI for very sensitive use cases, they're actually saying that they have to have some kind of transparency in the model, else they would rather be happy to use very simple linear models or very simple rule-based driven models. In fact, our experience was many people actually stayed away from deploying very complex ML models because they were black box in nature. That was one. And second, regulations are also not picking up. Meaning the AI Act in Europe, for example, they define very clear guidelines, or the guidelines are becoming more and more clearer. Like what kind of explainability has to be there for high-risk use cases. They divide the risk use cases into low, medium, and high. In low-risk use cases, you can use black box models, no issues. But as the use case becomes more sensitive, more important, it is now needed, or at least soon it will be needed to have explainable models as part of high-risk use cases. While everyone is excited about what ChatGPT or systems like LLMs can do, but nobody is comfortable to deploy something which they cannot understand. The current use cases are summarization and all of it. Even if you take summarization as a very prominent use case of LLMs, one of the recent problems with summarization is, what if it is not summarizing one of the key fact, right? Then I'm totally missing out that fact, because summarization may have taken different kind of route, but I would actually care about that missed out fact than what the summarization is giving out to me. Even summarization is still being questioned. So people are saying that use summarization as a reference, but not as the source of the decision-making process. I would say the need to use explainable AI is now becoming mandatory and more strong. as compared to earlier, which was primarily being used as a term, more like a good to have, but now it will soon become a must have kind of feature.
So I guess like I agree with you in that in my past experience. I've run this a lot. I've had people CEO level and a little bit below that tell me like why would I trust this model if I don't understand what's going on, right? Why would I trust my business to something I don't understand? These kinds of things. But kind of my question was more centered around the future, in that I agree with you in the past, this is how it's always been, but increasingly so, especially in the younger generation, people in my class, for instance, everyone I've talked to, they use ChatGPT, I use ChatGPT, and I tend to engage in a higher degree of automation bias with tools like that, where I just trust it more, right? And I'm more interested in a verbose explanation that actually gets my solution across the line more than I am a linked set with citations often. So I guess my concern is with explainable ML is less that we won't need it more, it's more that we just won't care about it in the future. And that was kind of where my question was centered around this idea of, do you think the future generations will simply engage in automation bias and explainable ML will be pushed to the wayside?
Yeah, I hope it's not the reality. Fingers crossed. I hope people are more, more leaned towards having transparent and controllable models. I don't think this would be the problem when you go to a bank or healthcare or all of that. They do not have urgency. They have urgency for sure, but they do not want to deliver automation, but not able to understand it. As I have given few examples, right? Experian, for example. So there is a strong demand to use ML model. And currently, we are at a phase where model manufacturing is happening at scale, which is the best. Meaning people are publishing models and want to put some model in production because they want to be using some kind of ML in the process. But when slowly such examples are coming out, players like Experian facing model failures, Zillow facing model failures, Apple having model failures, once such examples becomes more prominent, then people can understand that, okay, this is another feature that they have to include as part of the model as well. I don't know, I mean, we could have a feature where there is certain class of use cases where you would use explainable AI, and there is certain class of use cases where you may not need to use the explainable AI.
Thank you.
Okay, do we have any more questions from the audience? Okay, so I did have one question here talking about, I know you mentioned model debugging and security, so I was wondering, what texts or sources do you recommend to learn about these things? Because I haven't actually seen that before, even taught in courses, right, about debugging and security.
Sure. Okay. In fact, this is something that we are doing parallelly as part of our research as well. So what we do is we pick up a technique. One of the current techniques that we are using is synthetic and generative AI. In fact, synthetic AI more prominently because that applies to tabular data more actively. So what we are saying is, okay, synthetic AI is giving me synthetic data sets. Now, if I am an attacker, and if I'm a hacker, how do I attack this model, right? In ChatGPT, the same thing is happening as well. So there is prompt engineering. There is another technique called poisoning the training data, which means that do not use pre-trained models anywhere. Ensure that you know the source of the pre-trained models, because there is a way to pre-train a model with poisoned training data, and then later on exploit your ML models. That is one of the experiments that somebody has done and published about it. We were actually attacking the synthetic data to generate the PII information that the user might want to hide. So we were able to extract around 30-40% of PII information when we used GANs as GANs for synthetic data generation. So this is a growing area of research, attacking models for, let's say, exploiting the data leakages, or exploiting the decisioning gaps. All those kind of things. I think with ChatGPT, it's already happening. People are attacking ChatGPT. They're doing jailbreaking of the models. They're trying to, exploit a lot of things with such LLMs today in which I can actually send a few papers that we refer, which has actually talked about the examples that I gave. It's there in the earlier slide as well. I can send that as a material after this meetup.
Thanks so much. Okay. Is there any? Yeah. Okay. Go ahead. Thank you. Thank you so much, Vinay, for joining us. Our next